short, and I'm not going to explain why. So J is equal to twice of I. Okay. So we found I before, so J is twice of I. So now, as I said, the more important part is this positive shear or negative shear? Okay. So this is our shaft. I'm going to draw it big. Okay. So this is our axis. Now this is our element. Okay. Again, this is drawn really big. So this is our element H. If you look at the torque, just in 2D view, yeah. Okay, just in 2D view, the torque, if you view from the top, is pushing this way, right? So this is the 2,500 pound-inch. Okay. So when this is the case, right? Your element, again, we lock this side. Okay, we lock this end. If we don't lock it, no stress. Okay? And you look at the way the element will deform, because we lock the end, the element will deform this way. Okay, right? So this is our deformation pattern. Okay. Now, if the rotation has been reversed, okay, if the rotation has been reversed, okay, so I copy this, and I'm going to deliberately draw the rotation that has been reversed. Okay. So now over here, the rotation has been reversed. Okay, 2,500 pound-inch. And then if we were to draw our element now, right, and you will agree with me that the deformation pattern changes. This is now the deformation pattern. Okay, if we look over here. So this is our element H. Okay, this is our element H. So now, by looking at this, right, okay, I'm going to draw for you positive shear. And the next one is negative shear. If we look at positive shear, right, the stresses are acting this way, right, and then the deformation goes like this. This is positive shear. And then if we were to draw negative shear, and the stresses or the acting this way, this is now negative shear. Now, question for you guys, based on our actual problem over here as I circle, is it positive shear or negative shear?
Just negative shear?
Yeah, it's negative shear. Now, the next question asked is why this is so important, right? Why is it important to know whether this is positive shear or negative shear? Why? Okay, so now let's say the correct answer is negative shear. I'm going to sketch this out. Okay, just bear with me. Okay, and today's lecture, I'm afraid I'm going to give you a discount. What do I mean by that? I think it's going to go longer. Okay, give me until the most 9:15. Okay, but this is important. So now we know that why this is important. A lot of times I get asked by industry and by engineers why this is important. Why in solid is like you don't bother, in carbon fiber is so critical. So now, this is the correct one, okay? So we have compression and we have our shear. Okay, so this is the valid shear. Okay, and then we are going to draw the invalid. Okay, and by the way, I've seen this happen before where engineers did not care, and then yeah, boo-boo happens. Okay, they wrap the carbon fiber in the wrong direction. Okay, so this is the invalid one. Okay, so one side is the valid, the correct one. That's a correct based on our problem. Okay, correct based on problem. So again, yeah, it's straightforward. This is our point X. This is our point Y. And this is our point X. And this is our point Y. Now we start to draw mole circle. Okay, we start to draw mole circle. So again,
Wait, Eugene, why is one valid and one's invalid?
this is because, okay, the shear direction is negative shear based on the torque that's applied in this direction.
Mhm.
And in reality, this is the direction that's been applied, which is true.
Yeah.
Okay.
Oh, so you're just talking about in our case, not just
Yes.
all cases. Okay, okay.
Samuel, what question do you have? Sorry.
I just want to say, how do you know stress X was going in? Is it because
Yeah, because we did here already, right? Compression. Element H is on top, right? So it's in compression.
oh okay.
Okay.
And how do you know it was negative share? Or
So you see how the element is deformed, right? You see the pink line, the top pink, yes or no? This one.
okay.
Okay. Then you compare to the deformation pattern, right? So this is the same as here, right? So that's why it's negative shear.
Okay.
Okay. Okay. So now what if we mess up in the direction? Okay, so okay, we plot mole circle, we plot mole circle. Okay, we plot mole circle, we plot mole circle. Yeah. So the correct one, both circle, by the way, both circle, the principal stresses are the same. I repeat again, both circle the principal stresses are the same. So this is the normal stress, this is the shear stress, clockwise rotation, anti-clockwise direction. This is your stress Y, and then over here, okay, over here, this is your stress X. Okay, so this is your stress X. So we have our shear. Okay, so likewise, shear down here. Okay, then our, oh, I hope this work, man. It always don't work like this, you know. Ay. Okay. Okay. So point X, right? The element is rotating in a clockwise direction. This is point X. And then the other side would be a point Y, right? And this is your line that you draw, right? And then this is the circle that we draw. So I'm just eyeballing this, okay? So it's about 1, 2, 3 and a bit. Okay, so that is our mole circle. So this is our stress 1. That is our stress 2. Okay. So from X, okay, or from Y, we rotate our carbon fiber by 2 theta. Right? And 2 theta is anti-clockwise. Okay, so theta is anti-clockwise. So our principal stress direction, right, is this way. So from here to here, y to theta. So this is our theta. Okay, so this is our theta direction. Okay, so our lay direction from point Y is it. So we'll lay our carbon fiber in this orientation. Okay, so that's the real. Now, if you assume your shear in the wrong direction on the right hand side, right? So this is now your X, and this is now your Y, right? Now it gone opposite. Okay. Then I'm going to be cheeky down here. I'm just going to copy and paste to tell you that the principal stresses are the same. Yeah, the principal stresses are the same, right? Okay, Eugene, come on, focus. Okay, so the principal stresses are the same, right? This is your stress 1 and stress 2, right? So in non-carbon fiber world, you just need to know what is your stress 1 and stress 2 value, right? Either one, okay, either shear that you use, whether is it positive or negative shear, your stress 1 and stress 2 are correct. Okay, now this is only good for homogeneous material. Okay, for carbon fiber, now Y have to rotate clockwise by 2 theta. Okay, so basically now Y have to rotate clockwise by theta. The other one is okay. So the red line indicate the carbon fiber optimum direction. Can anyone tell me, is the direction the same? Anyone? Hello?
No, they're opposite.
Yeah, exactly. Is not the same at all. So on the right hand side, if you assume your shear in the wrong direction, how you wrap your carbon fiber is down the toilet bowl. Okay, but for non-carbon fiber like solid, like steel, all you need to know is stress 1 and stress 2. Stress 1 and stress 2. Right? That's all you need to know. So it does not matter. Once you know stress 1 and stress 2, you pick the right material, there you go. Okay, you assume that the stresses are isotropic, they are the same in all direction. In carbon fiber, it is not. Okay, I just proved to you why it's so important to know the shear stress direction. Once, if your shear stress direction is assumed wrong, you can wrap how much carbon fiber, and you will call me Eugene, carbon fiber is absolutely useless. Yeah, it's because the analysis is wrong, that's why it's useless. Okay, right. So coming back to where we are, so we calculate our torque now, right? So we know that it is what? We know that it is negative shear, right? So now the torque now is just putting in the formula is always the easy part. Understanding what it means is more critical than anything else, okay? So the radius is 1.25 divided by 2, and this is pi over 2, 1.25 divided by 2, power of 4. Okay, so the shear stress is 2500. Okay, hold on, 2500 power divided by 1.25 divided by 2 power